An AI scores 99% in training, then fails on new data. It didn't learn. It memorized. Neural made simple. Training examples are practice, not the final exam. In the next 5 minutes, you'll learn how to spot overfitting, why it happens, and 5 practical ways to reduce it. Overfitting happens when a model fits its training examples too closely. It learns useful signal, but it also learns noise and accidental details that will not repeat in the real world. The real goal is generalization, useful predictions on examples the model has never seen. A slightly lower training score can be much better if performance stays strong on new data. Here is the warning sign. Training loss keeps falling, while validation loss falls at first and then rises. When those curves separate, the model is improving at practice but getting worse at the real test. Imagine every training photo of a cat has a blue background. The model may learn that blue means cat. Show it a cat on a red sofa and the shortcut fails. High accuracy can hide the wrong lesson. One cause is excessive model capacity. A very flexible model has enough freedom to fit real patterns and random noise. Complexity is useful only when the data is strong enough to support it. Overfitting also becomes easier with too little data, duplicate examples, incorrect labels, or data from only one place or group. Better data means variety, accuracy, and a close match to real use. Another danger is data leakage. If a feature contains information from the future, or from the answer itself, validation accuracy may look amazing even though the model cannot work in production. Use separate training, validation, and test sets. Training fits the model. Validation helps you choose and tune it. The test set stays untouched until the end. For time-based problems, split by time. Look for a large gap between training and validation performance, unstable results across different splits, suspiciously perfect scores, or a sudden performance drop after deployment. Fix 1 is regularization. Methods such as L2, L1, and dropout discourage fragile solutions. They make it harder for the model to depend too heavily on one weight, feature, or pathway. Fix 2 is early stopping. Save the model whenever validation performance improves. When validation stops improving for several rounds, stop training and return to the best save checkpoint. Fix 3 is data augmentation. Create realistic variations such as small crops, brightness changes, or harmless noise. Use only transformations that preserve the correct answer for your task. Fix 4 is to simplify the model and strengthen the data. Try fewer features, less depth, clean labels, more diverse examples, and a simple baseline. More complicated does not automatically mean better. Fix 5 is cross-validation. Train and evaluate with several different folds. If performance changes wildly from one fold to another, your result may depend on a lucky split. Before trusting a model, ask, is validation genuinely separate? Could information be leaking? Do the learning curves separate? Is performance stable across groups? And does the evaluation data resemble the real world? Remember, low training error is not the goal. Learning a pattern that works on new data is. Next, we'll explain precision, recall, and F1 score. Subscribe to Neural Made Simple and keep learning one clear idea at a time.